Trying to find the volume of the torus, and I said that, practice some of your algebra because it's very easy to make little mistakes doing algebra. It tends to be the bigger problem in Calc 2, the algebra and the trig, and not so much the calculus. So I did the algebra here. So look at that, make sure you understand it. All we did was FOIL, and then distribute the minus sign. And it boils down to a couple of options. If you don't use symmetry, if we're trying to find the area of this entire shape here, we're going from -2 up to 2 if we don't use symmetry. So that's this one. And then if we use symmetry, we can go from 0 to 2 and double the coefficient out in front. The coefficient out in front is 12 pi, so it doubles to 24 pi. So that would be it using symmetry. Now I want to point something out here that's going to be important, and that is this integral, this definite integral, do you have the skills to integrate it at this stage? Does anyone have an idea of whether it's integrable with, so you really only have substitution at this stage. Substitution is your main integration technique. And my question is, can you integrate that with substitution?
Well, I got stuck, but it does look like the derivative of inverse sine, or inverse cosine.
It looks it looks similar to one of those. So we haven't done the inverse trig functions yet, but it does look similar to an inverse trig function, which we haven't done yet. So if you could find an antiderivative from an antiderivative table, for sure, that could work. What about substitution, though? Could you do it with substitution? If you were going to do a substitution, what would you let u equal? You'd let u equal whatever's inside the square root, right? That's the problem, is what's in the, when you do a substitution, you're usually letting u be what's in the square root, what's in the angle, what's in the exponent. So you're taking sort of what's the innermost piece and you're letting u represent it, and then you try to substitute. Well, if you did that here, what is the derivative of 4 minus y squared?
-2y.
So if you were to do this, when you do substitution, the derivative of whatever you let u equal has to be present. And there's not a y on the outside of the square root that you could then pair with the dy to change y dy into some sort of u expression. So substitution only works if the derivative of u is in the integrand somewhere, and it's not here. So substitution is going to fail us here. We will see a technique later that will allow us to do this. And it's going to be called trigonometric substitution, but we're not there yet. And the idea of an inverse trig function was mentioned. The big problem here is that the inverse trig function has that square root in the denominator, not in the numerator. So we can't use that correctly. So my question is, well then, what do we do? In this class, I really am going to try to emphasize a lot of geometry, and I'm going to point out something that is in the review for this chapter before the exam. So the review for this chapter, so let's see, where am I? Review, right there for chapter 6 and 7. I've got a bunch of examples here. At the very bottom is a reminder of what your definite integral represents in terms of semicircles. And this integral here, sometimes evaluating the integral is easier to do geometrically. Like if you know that the integral is representing the area of a semicircle, oh, just do pi r squared divided by 2, right? So if you have a circle, so look at this right here. So this right-hand curve is x equals that. The integral from -4 -4 up to +4 on the y's, this is going to give us the area on the right there. And I've got them all broken down. I've got 4 different ones broken down there, a right, a left, a top, a bottom. So you should look at that, because this should all be reviewed from Calc 1, where you're thinking about the definite integral as area beneath a curve, or the area, you know, we don't say beneath the curve when we're talking about a function of y, but you know what I mean. Between the y-axis and the curve instead of between the x-axis and the curve. So these are the two that you're more familiar with. So look at those just as reminders. And what I want to do with this torus problem is I want you to notice that this, let's go to the one with symmetry because we have a 0 in the limit of integration. That's a little nicer. What I want to do is this. I want you to think about this. Okay, this curve right here, if we look at this, this is x equals the square root of 4 minus y squared. So let's figure out what geometric properties this curve has. All right, let's go. So we can square both sides and add the y squared to the left. Oh, that's a circle of radius 2 centered at the origin. And if you isolate x and you choose the positive square root, is that the right half of the circle or the left half of the circle? Like right here, if somebody said, hey, isolate x, you would end up with plus or minus the square root of 4 minus y squared, right? Whenever you take a square root, if you take the square root of both sides, you get a plus or minus. So x equals positive is going to be the right half. If it was y, if you isolated y, you would get a top half or a bottom half. Like y equals a positive square root to top half, y equals negative square root to bottom half. X equals positive square root is going to be the right half. X equals negative square root is going to be the left half. So is this the right half or the left half?
Right.
That's the right half of the circle of radius 2 centered at the origin. So let's draw that. So if we look at the right half of that circle of radius 2, so we're sort of like that. Now the y values are only going from 0 up to 2. So there's 2, there's 0. So what part of the right half of the circle is this finding?
Top.
Just that top quarter. So this integral right here, this integral right there, is that area. Oh, well, we know how to find the area of a quarter circle. This area right in here is going to be pi times r squared divided by 4. Pi r squared is the area of the full circle. So that integral's value is pi, because that integral is representing the top half's area of the right half of the circle. And so that's how we can do it geometrically. So there's times where we can do things geometrically pretty easy, and there's times where we have to just do the integral, because that's easier. Most of the times in this class so far, we've seen that it's way easier to find the area with an integral, because you have some weird shaped region that you don't have a geometric concept of. But circles, we know circles really well. So the area integrated is going to give us this for the volume. That will be our volume, 24 pi squared. Okay, so look at that one carefully. That reveals a lot of technique and a lot of algebra and a lot of geometry. So look at that carefully, and if you have questions on it, we can talk about it during the break or whenever. Okay, so let's go back to our shells and do some more shells. So our big concept here is that we're trying to find volume by integrating a cross-sectional area function. Typically, we visualize cross-sectional areas like, by taking perpendicular slices. But when we do shells, our cross-sectional area, we're thinking more like an apple where we're coring it. And we're thinking about these concentric cylinders as our cross-section. So it's not technically a cross-section in the traditional sense. So let's take a look at this curve here, or this region. This is a region. Regions are spaces in the xy plane. And then that region in the xy plane is going to get rotated about the x-axis, and it's going to create this shape down here, that solid object. And I have one cross-section revealed down there. So there's our random vertical element. Ooh, should I be choosing a vertical element or a horizontal element? If we're trying to create a cylinder, horizontal, right? Because if we want to create a cylinder, that element has to be parallel to the axis of rotation. This would create what geometric object if this vertical segment was going to rotate around the x-axis? What shape is that going to create? A washer. That's a washer. So we don't want that. So we're trying to do a cylinder. We call them cylindrical shells. So we're going to choose a horizontal element at y, not a vertical element at x. So that red element there, this is going to be, that cross-sectional shell, that cylinder there. This sideways element, the height of it is sideways, okay? When we talk about the height of because we think of it as a thin rectangle, the height is sideways, and the thickness of it is going to be d what? X or y? dy. Horizontal rectangles, thickness is dy, vertical dx. So that is going to be giving us the following. So the area of our cylinder, or shell, we know the generic form for a cylinder is 2 pi r times h. 2 pi r is the circumference of the base, and then you multiply by the height, and that gives you the area. So we look over at our picture. Oh, the height is sideways. The height is this direction. It's the length of that red segment. Okay. And how about the radius? Well, the radius is the distance from your element to the axis of rotation. That is the radius. I'm going to put the height in red just so that we can kind of associate the height with that element. And the radius we'll use black for. Does everybody see that? So the radius is the distance that horizontal element is from your axis of rotation. So it's whatever that distance is. And then the height is going to be the difference between this right curve and this left curve. What is the left curve? We've got the right curve given to us right there. What is this left curve? Yeah, it's just a constant, right? X equals 1 over root 3.
Are we trying to find the volume?
We're going to find the volume, yes. But first we find the area of that region. So we set up area, and the concept is that integrating area gives us volume.
Okay.
So once we set up area, we'll get to volume by putting an integral in front of the area.
Okay.
So first we're thinking area. So that is the area of this red cylinder here. And then when we integrate, we sort of add up all of the cylindrical volumes. If you put thickness to your cylinder, then you have a slice. You have a volume. And then you add all the volumes up to get the total volume. So when we look at these, we have two concepts that we've looked at. Horizontal distance, x minus x. Vertical distance, y minus y. So vertical is a change in y's. Horizontal is a change in x's. Let's look at the first letter here, r. R is vertical. What is the y coordinate at the bottom?
0.
What is the y coordinate at the top? Y. Y minus 0 is y. So 2 pi y. Right? This y is measuring the distance to that axis of rotation. So that y value is the radius. If we call that number right there y, how far away is it from the x-axis? Y units. So it's representing the radius of that cylinder that's being created there. Now h. H is horizontal. That means we need an x-coordinate on the right, an x-coordinate on the left. Take the difference. The x-coordinate on the right, it's the function. The x-coordinate on the left is this constant right down here, 1 divided by root 3. So this line segment that's the curve on the right, so this curve is the constant function 1 over root 3. And that is the left curve. Even though it's straight, you know, it's a line, it's still a curve. Curves don't have to be curvy, they can be straight. So that is the left curve. So when we come in to find our height, the right x-coordinate minus the left x-coordinate, that is now the area of the cylinder at y. So you plug in any y coordinate, any y value between 1 and root 3 into there, you'll get the area of the corresponding cylinder. All right. So now we have to integrate that. So volume is the integral here, so we can factor out the 2 pi. We'll talk about our limits of integration in a second. We're going to distribute this y across, and what I notice is that when we distribute the y, in this first place there's a cancellation, and then over here, 1 over root 3 times y, or you can put the y in the numerator, it doesn't really matter, whatever helps you integrate more easily. And then our limits of integration, should they be y limits or x limits?
X.
You think? Is the element horizontal or vertical?
Horizontal.
So if it's horizontal, is it sliding along the y-axis or is it sliding along the x-axis?
Y.
So the limits are going to be y values then. The element is always perpendicular to the interval that you're integrating on, because you're thinking to yourself, no matter where you draw this red representative rectangle, right, it's got to be in the interval that you're integrating on. So there's cylinders from 1 up until root 3. So that element's always going to be perpendicular to that interval that you're integrating on. So our limits of integration are going to come from the y-axis, 1 to root 3. 1 to root 3. There we go. So now this one is also an integral that we can't do with substitution. If you let u be the denominator, you get a derivative of 2y, but there's not a 2y in that integrand, so we can't use substitution. Substitution only works if the derivative of u is present. There is no y in the numerator to absorb a 2y as a derivative, so we can't do that. Now, this one, though, does have an antiderivative that is in the antiderivative table, and we're going to see this one a ton. It's the most commonly used inverse trig function. So we know that the integral, well, you know that the derivative of inverse tangent is 1 over 1 plus whatever the variable is squared. So 1 over 1 plus x squared, 1 over 1 plus y squared, arctan, inverse tan. So this one is going to integrate directly to 4 as a constant, and then that's going to be inverse tangent of y. And then this one is a y squared over 2 thing. So we're going to have that. And then our limits of integration, 1 and root 3. And now we do the fundamental theorem of calculus. Plug in the upper limit, plug in the lower limit, and take the difference. So this is all going to be found by, and you could distribute this 2 in if you wanted to cancel out that 2 there. There's all sorts of constant manipulations you could do. Doesn't matter. It's totally your call if you want to do that or not do that. So first we're just going to plug in root 3, and root 3 squared, of course, is 3. So that's the upper limit of integration plugged into the antiderivative. And then we subtract off the antiderivative evaluated at the lower limit of integration. The lower limit of integration is 1, and we're going to put these in parentheses here just because we want to be careful with any negatives. And when you put the 1 in there, 1 squared is 1, so we still just have 1 over 2 root 3. Okay. So next, we have the function arctangent. Whenever you see an inverse trig function, the first word that should come blazing into your head is angle. Anytime you see inverse, sine, secant, tangent, whatever, angle. That's the first word that should come into your head is angle. So this says, what is the angle? And we have to be careful because we have 3 different places that inverse trig functions live. So we have 3 different scenarios. Inverse tangent lives on the right. On the right means between negative pi over 2 and pi over 2. Inverse cosine lives on top, angle between 0 and pi. Inverse sine, like inverse tangent, is on the right. So you need to know where your inverse trig functions live. So these are the 3 places that they live. So when you see this, you say to yourself, angle on right that has a tangent value of root 3. That's what that says. That says the angle on the right with the tangent value of root 3. So now we think right side of the unit circle, tangent value has to be root 3, so it's in quadrant 1 because it's positive. Down below, tangents are negative. And when you're talking about the unit circle centered at the origin, tangent is the same thing as the slope of the line through the origin. Same as the slope of the terminal ray.
Just a really quick question about the algebra. You did times 3 and not times the square root of 3.
Well, the square root of 3 is squared, which makes it a 3.
Okay.
So when we plug in root 3 right there, root 3 squared is going to be 3. Root 3 times root 3 is 3.
Yeah.
Does that make sense?
Yes.
So what angle has a tangent value of root 3?
60 degrees.
Radians, we're in calculus.
Oh, gotcha. That would be pi over
5 over 3? 5 over 3. 5 over 3. In algebra, we do use degrees quite a bit because degrees are more relatable. If somebody says, oh, we're going to launch this at 20 degrees, you can visualize that more easily. Visualizing radians is really hard. But when we get into derivatives and integrals, radians are better because they're unitless. We can talk about that later if that doesn't make sense to you. So that angle is pi over 3. On the 12-sector unit circle at 30 degrees or pi over 6, that slope is root 3 over 3. The steeper one up at 60 degrees or pi over 3 radians is root 3. So slope here is root 3, slope here is root 3 over 3. What about here? Slope is, so this says the angle on the right with the slope of 1. The angle on the right with the tangent of 1 is the same as the angle on the right with a slope of 1. And what angle in quadrant 1 has a slope of 1? Pi over 4. Yep. So that gives us our 2 angles that we plug in here. So we have 4 times pi over 3 minus, I'm going to get a common denominator. I'm going to rationalize this denominator. It's looking very messy not having it rationalized. So I'm going to multiply top and bottom by root 3. So multiplying top and bottom by root 3 will eventually cancel that 3. And then this is minus 4 times pi over 4 plus 1 over 2 square root of 3. But again, let's rationalize that. So that's going to be 2 root 3 over 3. It'll be easier to combine them. So we have this scenario. I will write the algebra simplification later. I don't want to spend time just adding fractions. Much more important concepts to deal with. But I will add them up during the break or something. So any question on the calculus part of it?
I have a question.
Mm-hmm.
In determining the R, could you explain that? Why don't we need to subtract,
Upper minus lower?
Yeah.
So in this case, the axis of rotation is at y equals 0, right? So that's the easiest scenario because we don't have to literally subtract off something. But so the axis of rotation is sitting right here. This distance is what we're curious about. And we say to ourselves, okay, that distance is vertical. Any vertical distance, we need the upper y coordinate, the lower y coordinate, and we take the difference. That's how you find a vertical distance, right? If this was 1 and this is 5, the distance is 4. You do the upper y value minus the lower y value to get a vertical distance. When we look at this, the lower y value is 0. The upper y value is whatever comes over to here, and it's a variable, right? It depends on where you drew your element. If you drew your element here, that would have a different y coordinate than if you drew it here. And so that y value represents a number between 1 and root 3. And so as we do the integration takes care of all of the y values between 1 and root 3. So that radius is variable. It changes depending on the cylinder. Cylinder could be radius 1, radius 1.1, 1.2, all the way up to radius root 3. So that y coordinate is representing all the possible radial values for all the possible cylinders.
So then we take care of that with our limits of integration.
Mm-hmm. Yes, exactly. So the limits of integration then fill in the blanks for all the possible radii. So no matter what radius value you have between 1 and root 3, those limits of integration take care of all those. So it's going to literally take care of all infinite possible cylinders. Yeah, it's amazing. All right, so let's try another one. So these shells, and again, the shells are tricky because you have something happening horizontally and vertically simultaneously. So there's a little bit more ambiguity. So you've got to be really good about thinking clearly about, oh, this is vertical, y minus y. This is horizontal, x minus x. So here we're going to rotate a region around a different axis of rotation, not an x or y axis. So right there is our axis of rotation. That's what we're going around. It's way over here at -2. There's our region. And it's generated by y equals x squared, x equals 1, and y equals 0. Those are the boundary curves. And it's going to rotate around, and we're going to use a cylinder. So cylindrical shells, we're going to use a vertical element. So this part is super important. If you want a shell, your representative rectangle, your representative element, whatever you want to refer to it as, has to be parallel. To create a cylinder, the element and the axis have to be parallel. If they're perpendicular, you're going to create a washer if there's a gap, or a disk if there's no gap. Right? So if we want to create a cylinder, parallel. So we've drawn this element here parallel. So there's our element at a random x. Vertical elements are at a random x. Horizontal elements are at a random y.
Can you say what it's parallel again to?
It's parallel to the axis of rotation. So if we look at the axis of rotation, that's what dictates our shape. There's our axis. If we take something that's perpendicular to it, it's going to create either a washer if there's this gap, or a disk if there's no gap. But if our axis of rotation and our vertical line are parallel, then when it rotates around, it's going to create the cylinder. It's going to create a can. So that's what's parallel. So we're either parallel or perpendicular to the axis of rotation. The axis of rotation is sort of our anchor to the problem. Because now we have to find the radius with respect to the axis of rotation, the height with respect to the axis of rotation. Everything's sort of focused on that axis of rotation. So when we look at the radius is the distance between the axis of rotation and our element. And then our height is the height of that element. And we know that the area of our cylinder is 2 pi rh. Are we trying to turn the R and the H into X's or into Y's? Into X's, because this is a vertical element, and how thick is a vertical element? dx. That tells us that the integral is going to have a dx in it, which tells us the integrand can only have x's. We can't have a y with a dx. Not yet. Not until Calc 3. So the goal here then is to turn the r and the h into expressions of x. So we look at the radius. Radius is going from here all the way over to here. There's the radius. Is that a horizontal distance or a vertical distance?
Horizontal.
So should we be subtracting x's or y's? X's. So we need to know the right x, we need to know the left x, and we need to take the difference. What is the right x? X. That's what we called it. And that's moving between 0 and 1. So it's just representing any vertical element between 0 and 1. What is the left x? Negative 2. So it's x minus minus 2. So x plus 2. That is the distance. Let's think about it visually. What's this distance between the y-axis and the axis of rotation? 2. And then what's the distance here? X. Right? The distance between 0 and x is x. So x plus 2 would be the total distance then. So you can think of it geometrically that way, or analytically as right minus left. So you can always do it really formally. The right x coordinate is x, the left x coordinate is negative 2, so x minus minus 2. And then what about the height? The height in this case is
X squared.
just x squared. So that is a vertical distance. So we want a y-coordinate on top, a y-coordinate on bottom. We want to take the difference. Well, the y-coordinate on the bottom is just 0, because it's on the x-axis. The y-coordinate on top is the function, x squared. So that is our height. And if we distribute this, we are going to get our area function simplified. And to find the volume of the seats in this Colosseum, we're just integrating. So we're going to integrate 2 pi x cubed plus 2x squared with respect to x. Limits of integration are, so look at your vertical element. The vertical element is sliding across your region
0 to 1.
0 to 1. Those are our limits of integration. And then pretty easy definite integral here, because we just do the power rule. Add 1. No trig functions. So we get that. And we'll get 2 pi multiplied by 1/4 plus 2/3 minus 0. So whatever that simplifies to, that will give us our volume. Oops. So our final volume is going to be 11 pi over 6. That will be our volume. All right, any piece of that you want some extra chatter about? Yeah?
So that eighth slide, could you explain the rotation, what's happening here?
Right here?
Yeah, with this question, like, I don't understand what it's rotating around, but.
So the line x equals -2 is the axis of rotation. So we have this vertical line here, and we're going to take this and we're going to rotate it around x equals -2. So in this picture, you can see x equals -2 is right there. This generating region is over here just to the right of the y-axis, and when it rotates around, it's going to create this Colosseum-looking thing. But that central line is at x equals -2.
Okay, so what is the significance of that red line that we named X?
This one here,
Yeah.
that is the x coordinate that shows this red cylinder. So that red vertical element right there, when it rotates around x equals -2, is creating this red cylinder that's buried within the solid object.
Oh, but there are infinite X's in that?
Uh-huh.
It's just one of them?
It's just one of them. So all we can, like if somebody said to draw all of them, it'd be really hard. So we draw one representative. So we're thinking that no matter where you, so if we're each drawing one representative vertical rectangle, vertical element, you know, somebody might draw theirs over here, somebody might draw theirs over here, but the integration is going to take care of all of them. But we're only going to draw one, right?
Yeah, having trouble like understanding how you got the radius.
So the radius, yeah. So it's the distance from the element to the axis. So it's this distance between here. Okay, so that is a horizontal distance. So if we were on the x-axis and this is -2 and this was 5, what would the distance be? 7. We would do 5 minus -2. If this was 3 and this was -2, what would the distance be? 5. So you did 3 minus -2. If this is x and this is -2, x minus -2 gives you x plus 2. So we're still doing right minus left. Right? It's just that there's a variable in there, so it feels a little bit, you know, a little bit different. But that's all we're doing is subtracting right minus left.
If this was rotating around the x-axis, that would be turning into a disk problem, correct?
Correct.
Okay.
If this region rotated around the x-axis, it's touching the x-axis. So as it rotates around, it'll create cross sections that are disks.
And if it wasn't touching, that would be a washer.
Then we get a washer. Yeah, that's right.
Hypothetically, could I use a washer to find?
Yes.
Yes. Okay.
Yes. If you chose a horizontal element, you would be creating washers, and you could do that here. This region is both vertically simple, because you can draw a vertical rectangle and have a common upper and a common lower curve. It's also horizontally simple, because there's a common right curve and a common left curve. Now, if we did do washers, you would have to take this curve and solve it for x, because you'd be measuring horizontal stuff then. So, but yes, you could do that.
Just one more question. If
Yeah.
you rotate this object around the x-axis at 0, would the volume be the same?
No. No. Yeah, if we rotate this around the x-axis, we're going to get a lot less volume.
Oh, sorry, I mean around the y-axis.
Oh, around the y-axis.
At
We would
0.
we would still get less volume. So if we rotated around the y-axis, it would be there'd be no floor, right? It would come down to a point.
But the area is still the same, right?
The area is the same, but if you take if you take the area of my hand and you rotate it around right here, versus you take the area of my hand and rotate it around here, you're going to get a bigger volume. So your cross-sectional area can be the same, but that axis, the distance to the axis of rotation is going to dictate what the total volume will be. Make sense?
Yes.
Yeah, yeah. Okay, let's take a look at this guy. Same region, but we're going to rotate around y equals 2. So we're going to rotate it this direction. Y equals 2. Horizontal element, we're going to do shells. If you chose a vertical element, you'd be doing washers. This is a horizontal element at a random y. As it rotates around, it's going to create a cylinder. We know our generic cylinder area. Our generic cylinder area is 2 pi RH. So let's figure out where those things are in this picture here. So the radius is this distance right there. Oh, I don't know why. I should use it. I'd like to try to use the same color, but. So red, let's use red for this radius, I guess. So this radius right there That's the radius. It's the distance from the axis of rotation to our element. The height, I'm getting confused with my colors. So there's the height right there, that direction. Change in the color of the radius. I want that to be something different than red. Let's go with green. So the radius is going to be the distance between the axis of rotation and the element. The height is that direction. So the radius is always the distance between the axis of rotation and your element. It's the distance between them. And then the height is whatever the length of your element is. Now, are we going to end up with a dx integral or a dy integral? dy, right? If we have a sideways rectangle, the thickness of that is a dy, so that tells us we're going to have a dy inside the integral, which tells us that we're integrating with respect to y, which tells us this r needs to turn into y's, this h needs to turn into y's. We can only have y. Y is our integration variable. So let's look at this. All right, so the radius. Is that radius vertical or horizontal?
Vertical.
Change in y's or change in x's?
Why?
Y's for vertical. The upper y value is 2. The lower y value is y. 2 minus y. That is the radius. Change in y coordinates. The upper y coordinate's 2, the lower y coordinate is just y. How about the height? Is it horizontal or vertical?
Horizontal.
Horizontal. So subtraction of x's or y's?
Wise.
X's. Horizontal element, horizontal distance, x minus x. X minus x, so right x minus left x. So that red segment is horizontal. So we need to know that x coordinate, and take the difference. What is the x coordinate on the right?
1.
1. What is the x coordinate on the left?
Square y.
So let's look at the curve. It's a function over here. So if we look at this curve right there, that was y equals x squared. That's presented as a y value, so it's measuring vertical, not horizontal. So if we want to know x, if we want a horizontal measurement, we have to solve for x. So we get x equals plus or minus the square root of y. Are the x's in this interval ever negative?
No.
These x's are positive, so this is going to be the x value of any point along this curve. If you plug in the y value between 0 and 1, this x value is going to measure how far away you are from the y-axis. So the x value on the left changes. It's going to be equal to whatever square root of y is. So the x value on the right is always 1. The x value on the left is variable. It's different distances from the y-axis, and that's what this represents. So it's going to be 1 minus square root of y. So 1 minus root y, that is our height. The right x value minus the left x value. And if we multiply this out, if we do some foiling, we're going to get 2 minus 2 root y. And then if we distribute the other thing, the other term, we get that. And then we have nothing left to do but integrate. So you guys told me we're going to have a dy. I'm going to put it way over here. Those y values are going to go, so if this is a dy, that means you should look on the y-axis to get these limits of integration.
So 0 to 1.
0 to 1 from the y-axis, not from the x-axis. And let's write this in descending order. And I'm going to write that y to the 1/2 instead of square root of y. It's a little easier to do the integration. So we'll do our power rule for integration. Add 1 to the exponent divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent. Divide by 3/2 means multiply by 2/3. Add 1 to the exponent. Divide by the new exponent. We have that. Fundamental theorem of calculus, plug in the 1, plug in the 0, take the difference. When we plug in 0, we get 0. So that's not going to give us anything. So we just have some crazy arithmetic to do here. We'll have 2 pi, 2/5 minus 1/2 minus 4/3 plus 2. That's going to be over 1. We'll get a common denominator. I'll do that arithmetic during the break. All right, any piece of that brings you joy? Bad question.
How did we, can you just reiterate how we got the height to be for this group?
So when you look at that height, that's that red segment. Is it horizontal or vertical? Horizontal. And so anytime we're trying to find a horizontal distance, we do a difference in x coordinates. So if we're on the x-axis, and this is 3, and this is 7, it's 7 minus 3, which is 4. So we look at that red segment, and we say, what is the x-coordinate of the right? And the x-coordinate of the right point is 1, no matter where it is. So the right x value, no matter where you drew this red segment, the right x value is always 1. The left x value is going to be a function because it's changing, right? These x values for these green dots that I drew are all different. So that's why it's a functional representation. So the left x coordinate is this curve solved for x.
So it'd just be like right minus left.
So right minus left. So the right x is 1, the left x is square root of y.
Okay.
Yeah.
The square root of y, does that cover the distance from the y-axis to
Yes.
that?
That's right. So that function is measuring this distance across to there. So if you want this whole, so this is like, so if you're trying to measure, so here's kind of what we're thinking of, this kind of thing. So that square root of y is measuring that distance, the 1 is measuring all the way across is 1, all the way across is 1, and then square root of y is measuring to this curve, and then the height is right there. The height is this distance from there to there. So if we want the height and we know the total is 1, 1 minus square root of y will give us the h, right? So it's that kind of, that's a good visual to see it. Oh yes. The napkin ring. Some of you may not even know what a napkin ring is. So, does anyone not know what the napkin ring is? So napkin ring is it's a sphere where we drill out a hole. In the old days, like people my age, their grandmothers always had their napkins in these rings on the table. You didn't just slap your napkin on the table. Put it in a napkin ring, and the napkin was cloth. So you might hear that in a history class. I don't know anyone that uses a napkin ring anymore. So anyway, this shape is called a napkin ring. A sphere with a cylindrical-ish piece drilled out. Yeah, so it's like a bead. And we want to find the volume of this bead. So there's a top view of the bead. Looking at the front, you can kind of see that, okay, there's a hole in the middle. And the generating shape for the bead or the napkin ring is going to be that shape right there. And that shape is coming, this outer circle is a circle of radius 6 centered at the origin. So let's come down to here. So circle of radius 6 centered at the origin. If we want the right side of the circle, we're going to solve for x and choose the positive square root. The left side of the circle would be solve for x and choose the negative square root. So there's the equation of the circle. And if we solve for, I don't know why that's off to the side there. So that is the top half. So right half is positive x. Left side is negative x. Top half is positive y. Bottom half would be y equals the negative square root. So we're using shells in this section. So I'm going to choose actually the element. If this is going to rotate around the y-axis and I want to create a shell, it's got to be a vertical element. If we're going to use a shell, so it's parallel. So axis of rotation is right there. We choose a vertical, and that's why I solve for y here, because this vertical element is touching the top half of the curve. It's also touching the bottom half of the curve if you drew it all the way around. But if we just rotate the top half of the curve, we can then double it with symmetry. The top half of the bead doubled will give us the total volume of the bead, of the napkin ring. And because that element is vertical, is it a dy or a dx? It's a dx. So then everything needs to be turned into x's, which if I solve for y in this equation, that positive square root function is the top half of the circle. So the top half of the circle right there is going to be y equals the positive square root of 36 minus x squared. And then with our element, our element's height right there is the blue. And let's go with purple. The radius is going to be this distance from there to there is the radius. So once again, if we do a shell, the area of a shell, or a cylinder is what we've been calling them, area of a cylinder is 2 pi RH. And we know we want to turn everything into x's. What do you think so this vertical element that we draw, anytime we draw a vertical element, it's at a random x, horizontal element at a random y. So this vertical element, I'm going to put an x right there, it's at a random x. So what do you think the radius is? X. That's the radius. That's how far we are from the axis of rotation. The axis of rotation, we're rotating right around the y-axis right there. If we rotate that shape around the y-axis, we're going to get the napkin ring or the bead. And how about the height? So the height is vertical. That function represents the distance from the x-axis up to that circle. So that is going to be the height. All right. And so then the volume will be 2 multiplied by the integral of that area. So this element is just covering from the x-axis up to the curve, so it's only going to create half the napkin ring. So we need to double it. So this 2 out in front is symmetry. That is by symmetry. And then we're going to have the pi. You can bring the pi out. I'm going to leave the 2 from over here inside for a moment to show you something. And this is going to go 0 up to, or over to, I guess I should say, because we're integrating with respect to x, and we're not going from 0. We're going from 3 to 6, yes. Thank you. Okay, now this square root, we saw with the torus square root, we couldn't do it with substitution. The torus one, when we looked at the inside of the square root, its derivative was not around. What about here if we try substitution? Can we do substitution here? So we have 36 minus x squared. If we take that derivative, we get minus 2x dx. Ah, that is present, right? We have 2x dx right there. So if we isolate the 2x dx here, so in other words, just divide by minus 1, we have 2x dx, that's negative du. So that's how we can do it with substitution. So we will end up with, we have 2 pi on the outside, and then the integral is changing. This is going to be the square root of u. We're plugging in 36 minus x squared for u. And then 2x dx is negative du. So we're going to have a negative du. So there is our new integral. Now we have 2 choices. We can convert the limits of integration as well, or we can go back to the original limits of integration later. In this case, it's pretty easy to convert the limits, and there's nothing instructional that I want to show you, so let's just convert the limits. What do we get when we plug in 6?
0.
0. 36 minus 36 is 0. Plug in 3 and we get
B7.
27. Now, just as a refresher from Calc 1, do you agree that I could do this? I don't like having these integral limits backwards, going from 27 to 0. It's like looking in the rearview mirror for too long. Doesn't feel right. So 0 to 27, but then what do we have to do? Multiply by negative 1, and that will just take away this minus 1 right there. So we could do that. Flip them and multiply by negative 1, and that negative 1 that's sitting in front of the square root of u just disappears. And now we can integrate. Now it feels a little better. So integrate, we get u to the 3/2 divided by 3/2, which means multiply by 2/3, 0 to 27. 0 is not going to contribute anything. 0 to the 3/2 is 0. So plugging in the 27, let's see, we have 4 pi over 3. Plugging in 27 here, it's going to be a little bit of work because 27 is not a perfect square. So this is going to be 27 to the 3/2. Let's do it step by step. This is going to be a little bit finicky. So we could cube the 27 first and then take the square root, or we can take the square root first and then cube it. I'll take the square root first because that shrinks the 27. It's easier to cube a smaller number. So the square root of 27. 27 is 9 times 3, so that's going to be 3 root 3. Bless you. So 3 root, bless you.
Thank you.
Done? My grandmother was always like 6 times. So if it came, it was coming hard. So square root of 3 times 3 for the square root of 27. Everyone agree with that? 27 is 9 times 3, so the square root of 9 is 3, the square root of 3 is the square root of 3. And then we have to cube that. So we are going to have 4 pi over 3. 3 cubed is 27. And then root 3 cubed is 3 root 3. If you take the square root of 3 and you cube it, square root of 3 times square root of 3 times square root of 3, 2 to the square root of 3 is turned into a 3. Then we get a cancellation. That goes away. And then we have 27 doubled is 54, doubled is 108. So 108 root 3. Something missing? Pi. So there's our final answer. All right, questions on any of the pieces?
Yeah.
Any questions? Yeah. Yeah, I got a question.
Where did you double it for the symmetry?
So that 2 right here is the symmetry. So this 2 is the symmetry. This 2 pi x is what came from above. So this 2 pi x is right there, the 2 pi x. So I just factored out the pi, because I saw that the derivative of this included a 2x, so I thought it'd be easier to leave that 2 on the inside. You don't have to though. If we pulled that 2 out and made that a 4, then we would have an x dx here, and then it would still work out the same, but if you can make it match, it makes it a little bit simpler. It's gonna make it match. Yeah?
How did you get 6 and 3 for the limits of integration?
So the limits of integration are with respect to x. So when we look at our picture, the x coordinate right there is 3. This vertical element is sliding from x equals 3 over to x equals 6. So this is a circle of radius 6, so that right endpoint there is 6. And then we're drilling out a hole that is radius 3. So that tells us that we're going from 3 over to 6. You see it?
Yeah.
Oh, good. Any other questions on it? All right, let's take a break. If you have other questions on it, you can go through it during the break. The napkin ring, the torus, all these cool geometric objects. Lots of fun.
Estaba trabajando en like the front
At least I'm better now.
Yeah.
Air Force.
Maybe just hit pause
Una
on this
bolsa de
thing.
un montón de plumas.
If it works. So we've been doing a bunch of stuff in three-dimensional space, finding volumes. We're done with finding volumes now. Done with finding volumes. Or I'm done with finding volumes. You probably aren't done with finding volumes. Hopefully this weekend, you'll be done with finding your volumes with discs, shells, and washers. We're going to go to arc length now. So arc length is an interesting beast. Sounds very simple. We just want the length of a curve. So we want to measure along the curve. If we have some curve, we want to just know how long it is. That's it. Sounds simple enough. Well, this is a differential triangle. dx measures a little change in x, dy measures a little change in y. ds is going to measure a little change in s. S is going to be the letter we use for arc length. So x is horizontal, y is vertical. S means along the curve. In Calc 1, I don't know if you grasped it deeply enough or not, but there's a difference between a differential and an increment. An increment is what we represent with the little triangle. And that triangle is the Greek letter for D. It means difference. So delta S means the change in S or the difference in S values. And you saw it in Calc 1, delta Y, delta X, those things. Now, sometimes the increment and the differential match. Sometimes they're equal. 99% of the time, when you see a delta X, it's going to equal the dx. So in Calc 1, when you were doing tangent lines, you always had dx and delta x set equal to each other. But dy was an approximation for delta y. So delta y means the exact change in the y values. Dy was an approximation. And you should have seen this graph like probably too many times, where you have your curve, and then you draw your tangent line right there. And then you have this little triangle right there. This is dx, this is dy. And then, so that's along the tangent line. The differentials come along the tangent line in Calc 1. And then you have the red dots, that one and that one. This down here represents delta x. It's the exact change in the x value between these 2 points, and these two are always equal. Delta x and dx were always the same. But this distance right here, I'll put it with dots, that distance is delta y, so that's the exact y change. The increment in y means the exact change in the y coordinates. But you can see by the picture that dy is an approximation for delta y, right? It's just an approximation for delta y. So typically what we do is say the independent variables, increment and differential, will be the same, and the dependent differential is going to approximate the dependent increment. So the letter on the left is the dependent variable. It depends on the independent variable. And the independent variable, we set the differential and the increment equal to each other, and the other one's an approximation. So that is from Calc 1. Similar here, we're trying to find S, and you can see that that ds is approximately equal to delta S, but it's not the exact value of delta S. If we had like a seamstress measuring tape, those round ones that are flexible, you could measure along the curve. We don't have that. We don't have an S-axis. We don't have an S-axis that's wrapped on this curve that we could say, oh, there's S equals 0, there's S equals 1.5. So the distance is 1.5. We don't have any information about distance along the curve. So what we need to do is go back and somehow find distance in terms of x or y, because that's what we know. Right? We know how to deal with x's and y's. We know how they work. So here's what we're going to do. So the idea is that we are going to create a, let's see, where do I want to start? Let's start with the geometry of this triangle first. So the idea is that if you wanted to find your arc length, if you knew S values, if we knew our S values like S sub A and S sub B, and we wanted to integrate ds, if you knew those, you could do it immediately. The distance would just be that one minus that one. Let me remind you, quick example. If you integrate from 1 to 4 dx, what's that answer? 3. If you integrate a differential, you get the difference in the endpoints. Right? That's going to be 3. If you integrate dx from 2 to 7, it's 5. Why? What's the integral of dx? X. From 4 to 1, which is 4 minus 1, which is 3. So the integral of a differential is always the upper limit of integration minus the lower limit of integration. So if we're integrating with respect to S and we knew S limits, we could just plug them in. But we don't know anything about S because it's bendy. It's on the curve. We just don't know anything about S. If we did, we could just do that. So what we need to do is get rid of that guy and convert it into x's and y's so that we can use what we're used to doing, rectangular coordinate system. So there is the thing that we're trying to get rid of, that ds right there. Well, look at this differential triangle. Yeah, we know the Pythagorean theorem. And if you solve for ds, take the square root of both sides. We'll choose the positive square root. Now here is algebra. So this, we know that if we had a differential, it can't be inside of a square root. That's not going to help us, right? You know how to integrate when the dx or the dy has no power other than 1. We don't ever integrate something with a square root of dx, right? Or a square root of dy. It's just dx or dy. So what we have to do is a little algebraic manipulation to somehow turn this ds into an expression that has a dx or a dy on the outside. So we use our fairy dust, which is multiplying by 1. In this class, we are going to use so much fairy dust. We multiply by 1 all the time to create a different look, but not change the value. If you multiply by 1, you don't change the value, you just change the way something looks. It's like a unit conversion. Right? If you change inches to feet or feet to meters, you're not changing the value, but you're changing what the number looks like. But you're not changing the value. Same thing. So if we multiply by 1 in here, no big deal. It's just 1 multiplied by 1 doesn't change anything. So now, when you multiply by that 1, this dx squared and this dx squared are common, so we can factor dx squared to the front. Well, the square root of dx squared is dx. And so that factoring plops it outside of the square root. And then what's left inside of the square root, this becomes a 1. If you factor out dx squared, you're left with a 1 here. And over here, you're left with dy squared over dx squared, which is really just dy dx quantity squared. And we know what dy dx represents. Dy dx is the derivative. So that is the algebra that's going to allow us to convert this ds integral into a more familiar integral with a dx or a dy. If you wanted a dy on the outside, instead of multiplying this term by dx squared over dx squared, you'd multiply this term by dy squared over dy squared and factor out the dy squared, and it would be a dy on the outside. So there's our new formula. That is arc length. Arc length on the x-axis from a to b, if you integrate the square root of 1 plus the derivative squared, that's going to give you your arc length. That's our new formula. That's for arc length. So let's try it. Let's try it on a line segment. That's an easy thing to find the length of. So that's our new formula. It's the first real new formula you've had this semester. I mean, we've integrated area to get volume. You could say that's a new formula, but it's not that. It's not like this. This is a real kind of unfamiliar formula. So that is arc length. We have to form that integral. So we've got our function right here. The only thing we have to do is take its derivative. What's the derivative of that function?
Negative 3.
-3. It's a line. Derivative of a line is its slope. So -3. And then we plug it in. So s. When we look at this picture, it says we are going to go from -3 all the way over to 2, which is right there. And we're going along the x-axis here. So there is our interval, -3 to 2. So we are going to integrate on the x-axis -3 to 2, square root of 1 plus the derivative squared. Well, that derivative squared is 9. Now we have this. Square root of 10, integral from -3 to 2 times dx. That's it. That's the arc length. And what's the integral of dx from -3 to 2? What's just this integral part? 5. It's the length of the interval. 2 minus -3. You integrate a differential, you get the length of the interval. Upper minus lower. So this will be 5 square root of 10. That is our length. So definitely we need this new formula to solve these problems. All right, let's try another one. So, get ready for some more algebra. So let's review a little bit of intermediate algebra. These two formulas look familiar to you? The perfect square trinomials and how they factor. If you go from the right to the left, you're foiling. If you go from the left to the right, you're factoring or unfoiling. Those make sense? The only difference between these two perfect square trinomials, the signs right there. Okay, keep that on the back burner. So, let's take a look at this function. I've got this curve. You would never be asked to graph something, this bizarre looking. It would be given to you. You should be able to take its derivative though. Y prime. So we know with our new arc length formula, we always need the derivative of y. So we have to take the derivative. Derivative of ln of x.
3 over x.
So 1 over x for ln x, but then we're going to multiply by 3 to get 3 over x. All right. And then when we take the derivative here, we are going to end up with The 2 is going to come down and cancel with the 2 in the denominator and give us a 12. And so that will be x divided by, x divided by 12. All right. And now we have to square this. The derivative is squared in our brand new arc length formula. The derivative is squared. So I'm going to come over here and square it off on the side. So I'm going to say 3 over x minus x over 12 squared. Notice this up here. I said it's a sneaky perfect square trinomial. So here is what I mean by that. When we FOIL this out, I'm not going to simplify it. So it's first term squared, and then over here at the end, when we square this, we're going to end up with x over 12 squared. And then the middle term is minus 2 times ab. This is a. Why is the board all of a sudden getting grabby? It was doing so well. Now all of a sudden it's getting super grabby. So that is A. This is B. Okay? So A minus B squared, right there, A minus B squared, is A squared minus 2 multiplied by A multiplied by B plus B squared. So B does not include the minus sign. So this minus sign is just separate. B doesn't include it, A doesn't, it's not part of the A or the B. That minus is not part of B. Okay, now you're tempted to square everything out and do all the simplification. Don't do it. Don't do it. So, I'm only going to simplify the middle term. When this middle term is simplified, what do we get with that middle term?
1/2 x. Oh no, actually not. This
There's 1/2. Negative 1/2.
Yep. Everything collapses, the x's go away, everything simplifies to the numerical part to 1/2. And there's a minus in front. So that. Everyone agree with that? Right, there's x over x, 2 times 3. This 2 is really in the numerator because it's 2 over 1. So that's 6 over 12, which is 1/2. All right, now, in our arc length formula, what do we do after we square the y prime? Add 1. So let's come over here and add the 1. So if we add 1, so I'm going to just say it on the side that we're adding 1. When we add 1, what changes? Right? That's the only thing that changes, right? Everyone agree? If we add 1, negative 1/2 and 1 can be added and turned into a positive 1/2. We agree with that? What is the only difference between this trinomial and this trinomial? The only difference is the sign. That's the only difference, right? This is identical to this except that we have a different sign. They both have a 1/2 in the middle, but one's a plus and one's a minus. This one is a perfect square trinomial, right? It came from, bless you, it came from A minus B quantity squared. So that is a perfect square trinomial. It factors into A minus B squared. Perfect square trinomials factor into A minus B squared or A plus B squared. That is a perfect square trinomial. The way we built it, it's forced to be a perfect square trinomial because we took A minus B and then squared it. So it must be a perfect square trinomial. But it's not obvious. In algebra, when you saw perfect square trinomials, they're really obvious. These are not obvious. This must be a perfect square trinomial because this one is a perfect square trinomial. And the only difference is that you change the sign from negative to plus. So how is this one going to factor? What is this going to factor into? If this one was a minus b squared, what's this one? Yeah, the only thing that changes is that. It's a perfect square trinomial, and that's how it factors. If you were to FOIL this all, if you were to add all these things up, make that x squared over 144, 9 over x squared, you're going to go down a rabbit hole, and you're going to be, the two of you that said on your questionnaires that you hate doing MyLab math are going to really suffer. So let's see what happens when we use this little observation that when we don't multiply everything out, look at what happens. The 1 plus y prime squared is a square, and that's sitting under a square root. And the x's are told 1 to 6. And then we have the square root of a square.
The cancellation.
Cancellation. We like it. But if you don't see this algebra, you will be banging your head against a wall. Okay. Integral of 3 over x is going to be 3 natural log of x. Integral there is going to be x squared over 24. So we get that. Plug in the 6. We get 3 natural log of 6 plus 36 over 24, which is 3 halves. Minus, what's natural log of 1?
0.
Natural log of 1 being 0, we agree? So if we plug in 1 for the natural log of 1 is 0. So that part's going to go away. And then when we plug in 1 here, remember we're subtracting, so we'll end up with minus 1/24. So this will be 3 ln of 6, common denominator of 24, so that's going to be multiplied by 12. Oh, I guess I shouldn't have simplified it. 36 over 24 minus 1 over 24 is 35 over 24. Okay, so that is a very particular case for arc length where you can use some perfect square trinomial knowledge to make the problem pretty simple, actually, as long as you understand your algebra. So when you did perfect square trinomials originally, you had things like if you had so if you had something like that, it's a little more obvious when you have just an x squared and you have a constant that's an integer on the outside. When you look at that, you can say, oh yeah, a is x, b is 2, and the middle term is 2 times x times 2, 2ab. You could spot them a little easier. And the way they taught them to you should have been, it's a perfect square trinomial if the middle term is 2ab. And here you can say, oh yeah, there's 2ab. Here, not so obvious that this middle term is 2ab. Not so, but it is. It's just not as obvious. Okay. Any questions on the algebra, the perfect square piece? Make some sense? Yeah?
I got lost when you went from the integral down to 3 ln of x plus x squared over 24.
So from here to here?
Oh, okay.
So the integral of 1 over x is natural log of x. The derivative of natural log of x is 1 over x, so then its integral is going to be natural log of x. Remember? Does that make sense?
Yeah.
And then this one is just a polynomial, so that the coefficient is like 1/12 times x, so then it becomes x squared over 2. And multiply the 2 by the 12. All right, let's look at another one of these arc lengths. So again, it's a perfect square trinomial. It's going to take a few of these before it sort of, I'll warn you, like on the exam even, I'll warn you if there's a perfect square trinomial. That's sneaky. So this one, we're going to notice a slight difference. This function is, I need to modify this slide a little bit, because this function is given to us as a function of y. So they've isolated x instead of isolating y, and the formula is going to change a little bit. So our arc length, when you factor out the dx, that's for a function of x. And if it's a function of y, we're going to rewrite this so that this is 1 plus x prime squared instead of y prime squared, and that's going to be a dy. So this is for functions of y instead of functions of x. Yeah. Change that because we already just did that example. So now we're going to do this example where we have a function of y instead of a function of x. We still take the derivative, square it, and add 1. We still have to do that process. That's not going to change. So let's find x prime. We've got this function. The first term's pretty easy. The 4 comes down and cancels, so we end up with y cubed. The second term, we've got to be a little more careful. I'm going to think of that as y to the negative 2 over 8. It's a little easier to differentiate. You could use the quotient rule if you're, if you're into that. But if you think about this as 1/8 y to the negative 2, that's going to be a little bit easier. So I'm thinking of it like that. So when we differentiate, the negative 2 comes down. That's going to give us negative 1/4 y raised to what power?
Negative 1.
Negative 1/4 y to
Negative 3.
negative 3.
All right.
Because we're subtracting. Remember, so the power here is negative 2. Bring down the negative 2 and subtract 1. So negative 2 minus 1. That's going to give us a negative 3. So there is our x prime. Now we're going to square it. So x prime squared. And here's where I'm saying, don't simplify it. Write out the square. When you have an a minus b squared, it's going to be a squared minus 2 times a times b plus b squared. So that is perfect square trinomial. This is your a. This is your b. And a minus b squared is a squared minus 2ab plus b squared. So take the a, square it, middle term, negative 2ab, so there's negative 2, there's a, there's b, and then plus b squared. Okay, and then let's simplify it. So you know that you have a perfect square trinomial when the middle collapses to negative 1/2. That's the only way that you get this sneaky perfect square trinomial. It's the only way. Because when you add 1, what we need to happen is that the only thing that changes is the sign of the middle term. And if you get a negative 1/2 and you have to add a 1, it's the only way, it's the only number you can add 1 to and get that kind of symmetry. Any other number you add 1, you're going to change more than just the sign. So negative 1/2, you add 1, you get positive 1/2. That's the only way that we can get this to happen. Right? Any other number, if you add 1, you are not getting something that's just on the other side of 0. Same distance from 0. So what happens here? Let's check out our middle term. If it's negative 1/2, we know it's the sneaky perfect square trinomial, and it's not worth simplifying anything except the middle term. Do you agree that these cancel?
Yeah.
Right? Y to the 3 times y to the negative 3 is y to the 0, which is 1. Or you can think of it as y to the 3 over y to the 3. And then 2 divided by 4, we get the half. Sneaky perfect square. So that tells us, we know right away that, oh, sheesh, this factors. That's a perfect square trinomial, just like that one was. So we add 1. When we add 1, we're going to get another perfect square trinomial. So now we're going to do 1 plus x prime squared. And when we add 1, here's where we see that, we add 1, the only thing that changes is the middle term. And it changed so that it just flipped the sign. So that means that this one factors into y cubed
Plus
plus
1/4 y.
that one. Bless you. And now we can put it in the square root. So our new formula for arc length, and this one is going to be s equals, they give us the y values are going from 1 to 2, so we're going to have integral 1 to 2. And then in here, we're going to have the square root of this. Squared dy. And then it cancels out. The square root and the square cancel each other out, so we end up with the integral of something pretty easy to integrate. Now, some of you have noticed a pattern. Some of you have noticed the pattern that this is the same as that, except that you change the sign to plus. On the test, you have to show work. That is your indicator that you've done it right. If you end up with the exact same thing as that derivative, you've got to show your work for points. So then this is going to integrate y to the 4th over 4. And then when we integrate that, we're going to add 1 to the exponent.
Y.
When we add 1 to the exponent, we get negative 2. So we're going to get y to the negative 2. And divide by the new exponent, so we're dividing by negative 2, so we're going to get 1/8 with a negative. And this will be from 1 to 2. So let's plug in the 2. That's 16 divided by 4, which is 4, minus. Plug in the 2 there. 2 to the negative 2 is 1/4. 1/4 divided by 8 is 1/32. And then we subtract off the antiderivative evaluated at 1, so minus 1/4 plus 1/8 when we distribute the minus sign. And I'll do that arithmetic later. All right, so any questions on any of those steps? So these perfect square, again, I'll warn you when there's perfect square trinomial in test, just so that you don't go down the rabbit hole of squaring everything out and getting totally confused. Because what is your instinct? When you multiply this out and you get y to the 6th, and here you get y to the negative 6, and there's a constant, your instinct is going to be to put the negative 1/2 on the far right, and you're going to have this thing written in descending order, and then you're going to not be able to factor it, because that just does not look like something that should factor. It doesn't, it's sneaky. Sneaky, the operative word. Very sneaky. All right, so let's look at a non-sneaky one. These ones will feel really much easier now. So this one is another one where we've been given x as a function of y. So for this one, s is equal to the integral from c to d square root of 1 plus x prime squared dy. That's going to be our arc length. They tell us that we're going to go from 0 to 4. So we know our limits of integration. Once again, we have to find x prime. So x prime, oh, there's the formula right there. I didn't have to rewrite it. So x prime is 3/2 y to the what? So bring down the exponent, subtract 1 from the old exponent. So if we have 3/2 as the original exponent, we subtract 1 and we get 1/2. Now we have to square this x prime. So that's going to be 9/4 times y. When you square it, square the numerical part. You square the square root, you end up with just a y. And then we have to add 1. So 1 plus x prime squared. There's no simplification here if we just add 1. So that is what is going to go inside this square root. So there's our, that's the integral. Technique of integration. Substitution. But when we look at this substitution, you would normally let u be this. Isn't this linear?
Reverse chain.
So we can use reverse chain rule. If that's linear, we could substitute, let u equal that, take the derivative, solve for du, plug it back in. We could certainly do that. But if your substitution is linear, we can use RCR, reverse chain rule. So let's do reverse chain rule. Way more efficient. So we take our blob, it's to the 1/2 power. So we make it to the add 1, divide by the new exponent. So we're going to take our blob, whatever it is, as long as it's linear, add 1 to the exponent and get 3/2. Divide by the new exponent, so divide by 3/2, which means multiply by 2/3. But then, what is the derivative of this linear expression?
9/4.
9/4. So chain rule, if you were differentiating, you would multiply by 9/4. But integrating with reverse chain rule, we divide by 9/4, which is the same thing as multiplying by 4/9. So we divide by the derivative, and that just turns into a multiplication by 4/9. So our answer then, we have 4/9 over here. We're going to multiply by 4/9. So we're going to get 8/27 multiplied by that. So that will be our, let's see, I forgot my limits of integration, 0 to 4. So there should be a 0 to 4 and 0 to 4. That was not a good 0. 0 to 4. So now we just have to evaluate that. Zero does give something here. A lot of times we plug in 0 and it doesn't matter. We get 0, but here it matters. So we've got to be a little careful. So we have the 8/27 out in front. And then we're going to have brackets, parentheses. Plug in the 4. 4 cancels, we get 9 plus 1 to the 3/2. So that's 10 to the 3/2. And what do we get when we plug in 0?
1.
I guess I don't need a huge, it's not that bad. Just 1, right? Except am I adding it or subtracting it? Subtracting. Right, so we plug in the 4, and then we subtract off what we get when we plug in 0. So when we plug in 0, we're subtracting off whatever we get. So we subtract off, plug in 0, we get 1 to the 3/2. 1 to the 3/2 is just 1. Is everybody seeing that? So we plug in the 4. The 4 cancels with the denominator. We get 9 plus 1, which is 10 to the 3/2. Right there. And then we subtract off whatever this is evaluated at 0. When we plug in 0, we get 1 in here. 1 to the 3/2 is 1, so we're subtracting off 1. And there's one more step that you'll see frequently when you have this very common exponent. You will see this written like that frequently. Let's make sure you understand that algebra. So if you have 10 raised to the 3/2 power, that's the same thing if you initiate the denominator of the exponent first. That gives you the square root of 10, quantity cubed, which means, the definition of an exponent, that means you're going to take the square root of 10 and multiply itself 3 times. Well, 2 of them multiplied of 10. So when you see a 3/2 exponent, it's super common to go through this and just write it that way. So if you see something like 5 to the 3/2, very frequently they're just going to jump to something like that and get rid of that 3/2 exponent. Is the algebra coming back? Gulp. Algebra. The algebra. Yeah. Calc 1, you just don't use the algebra as much as you do in Calc 2 or Calc 3. All right, so this one is not a perfect square trinomial. So why don't you all start this one. This one is a function of x with an x interval, so we're going to use a dx and a y prime. So you all start that one. And I will take roll while you have fun with algebra. Fatima. And Arnulfo. Cash. Nolan. That's right. Jack. Jordan. Bless you. Danny. And Chewy. And Brianna. Welcome back. Evan. Was it you, Evan? Were you the other MLM hater? Was it you or was it someone else?
I mean, I do hate it.
Oh, yeah. So there was 2 people that mentioned it. It's like, and Jose wants to know how not to hate it. Do your homework way in advance. And as soon as you get stuck, go to another problem and email me and say, hey, before I hit my head against the wall, throw me a bone. Lauren. And Yesenia. And Trevin. And Gilbert. Kishore. Bry? Yeah. You go by Bry or Brian? Either one. Either one. Yeah. Okay. Bry. Odell. And Peyton. And Dalila. Ben. And Alvaro. Not here. Jose is here. Ishmael is here. Reza is here. Laura is here. Sebastian is here. Erica is here.
So you have to do the one on the outside first, and then inside. And these are things to do. These are 2 things. There's a bunch of things. There's the idea. Yeah, so...
Oh, pensamiento lo vas a profe.
So we have to find the derivative, of course. We always have to find the derivative. Let's see if you found the right derivative. 2/3 times 3/2, those are reciprocals, so they multiply to 1. So we're going to get x squared plus 1 to the half multiplied by 2x. Chain rule. That makes sense? Remember the chain rule? All right. Then we have to square this. Let's see if you do this right. So when you square the square root, you end up with x squared plus 1. When you square a product, you have to square each part of the product. So you're going to end up with 4x to the 4th plus 4x squared. Does that look okay? And then you add 1 to that and take the square root. So we are going to end up with s equals the integral from 3 to 9. Square root, we'll write it in descending order. We're going to add 1 to this. We'll put it on the right, and that's a dx. Is that a perfect square trinomial? Does it factor? So perfect square trinomial, remember the middle term has to be 2ab. What is a? A is 2x squared. Remember, a is whatever is, so if we were to try to determine if it's a perfect square trinomial, we would think of that. That's how you get to that. 2x squared squared is that. And then the 4x squared is our mystery. And then this is 1 squared. So in this case, A is that. B is that. And is the middle 2AB?
Yes.
Yeah. The middle is 2AB. If we take A and multiply it by B, we get 2x squared. And then if we double it, we get that. So that is a perfect square. It's not a sneaky one. That is not a sneaky perfect square. That is a straightforward perfect square. So then the factorization is a plus b squared. So a plus b quantity squared. A plus b squared. Square root and the square wipe each other out. So we end up with 2x squared plus 1 dx. And then we integrate and we get 2x to the 3 divided by 3 plus x, and that goes from 3 to 9. Plugging in 9 is going to give us 9 cubed, but one of the 9's can be simplified a little bit by dividing out a 3. So we're going to end up with 9 squared, which is 81, multiplied by 6. So we're going to follow that? Because it's 9 multiplied by itself 3 times. One of them, 3 can cancel out, so it's going to be 81 times 6. So what's that? 246 or something? Somebody double check that math. Plus 9 minus, plug in the 3, and we get minus 18 minus 3. And then whatever that, yeah. Did I do it wrong?
For the 2 over 3x to the power 2 cubed, when you plug in the 9, I got, actually, let me do that real quick. I got 486.
I did too.
486? Ah, shoot. 486?
Yep.
Oh, man. So, what was I trying to multiply? 81 times 6? Oh, yeah, 8 times 6 is 48. I agree. Yeah. 8 times 6 is 48. Thank you. And then all this is going to simplify to something like 495 minus 21, which will be 474. Oh, calculators make arithmetic so much easier. All right, so I've got another sneaky perfect square up here for you guys to do on your own. So not many of you did what I asked you to do from Tuesday to Thursday, doing that algebra problem with the torus. So now I'm asking you again to do a problem from Thursday to Tuesday. try this perfect square trinomial and see if you can get to that answer. We've done a couple of examples, so hopefully that will give you a model to try to get to that one. Those perfect square trinomials are tricky. So, we have had very cooked up arc length problems. Like that sneaky perfect square trinomial, the function has to be absolutely, very, very precise for that thing to work. The one that we just did, when we squared it and added 1, we ended up with a perfect square trinomial so we could factor it and take the square root. Also very, very unusually lucky. Like if you just go out and start dealing with a random function and try to find the arc length, it's not going to factor like that. Most of the time you're going to end up with something pretty gnarly. So let's just talk a little bit about how you can do this on a calculator. Because you can do it on a calculator, you can do it in Desmos. Obviously this is not something that's, I'm not going to ask you to do this on a test to find the arc length with a calculator because you're not doing any math really. But I just want to make sure you understand how to do it. So we definitely need to take a derivative. Whenever we find arc length, we're going to take a derivative, and then we're going to square it and add 1. So we're going to get that. And our arc length, in this case, they tell us we're going to go from -1 to 1. And then it's going to be the square root of 1 plus 4x squared. And so this is more common where you end up with something that you just don't know how to take the antiderivative of. And we will learn some techniques where you could actually take the antiderivative, find an antiderivative for that. We're going to learn a technique called trigonometric substitution. But we're not doing that now. So if you go to any of your graphing calculator, Desmos, all we have to do is type int, and that creates our integral. And what do we say? We're going from -1 to 1, if I remember correctly. So you can do all this stuff right in Desmos or on your graphing calculator. So we're going to plug in 1 plus 4x squared. Did I get the limits right? And then we have to put a dx. Boink! There it is. Oh, yeah, so simple. Technology can be great. And so then, depending on your homework, it may ask you to round to a particular decimal point. Make sure you just pay attention if it says round to the nearest 10th or 100th or whatever.
Will we get graphing calculators on the test?
No. Yeah, there won't be a question like this on the test. Yeah, graphing calculators, everybody has a different one. Some people are really good at them. Some people have the calculus package, some don't. If you don't have the calculus package and your neighbor does, do you want to be taking the same test with those calculators that don't do the same thing? No. Yeah, so it's way too complicated these days. Too much work.
Like scientific calculator.
Scientific calculator, yeah, there they are. Yeah, you can use scientific. Anything that doesn't have an integral button. So there is that one, I forget who makes that one. It's a Casio that does have an integral button that a lot of people have. So as long as there's not an integral button, you can use it. But you can't use one with an integral button. So pretty straightforward though, if you're going to use technology to find the arc length. This one, once again, we're going to take the derivative, and then we have to square it and add 1. So we always square and add 1. We don't even have to square it out if we're going to use technology, right? We could just not square it out because Desmos doesn't care. Desmos don't care. So we'll integrate 0 to 4 and then the square root of all this. I am going to multiply it out. I have to. So 4 squared is 16 plus 1 is 17. And then the middle term is minus 8x doubled, so minus 16x plus 4x squared dx. So that. Then we'll just plop it into Desmos, get our arc length. Oh, there's a 4x squared already in there. How convenient. So 17 less 16x. All right, we're there. That's pretty simple. Okay, so arc length in general, you can come up with some pretty gnarly integrands that you just can't integrate. So the ones that you're going to do on the test, good luck driving to Denver. Thank you. The ones you're going to do on the test, they'll either be the perfect square trinomial type, or you'll have the ones that just don't require something crazy. The worst integrals, if you talk to people that have taken Calc 1, 2, and 3, the worst integrals are the arc length integrals in general. Those are the ones that people sort of dread, arc length. We're going to do surface area next, and surface area is a little better than arc length because we're going to see that with the surface area integral, there's going to be there's going to be something on the outside that might allow us to use substitution. Like our problem with a lot of these is that the derivative here is 8x, and there's no 8x on the outside, so we cannot use substitution. And with arc length, there's never anything on the outside, so that's always the problem. So let's take a look at surface area. And surface area will be a little bit different. So first off, the only surface areas we're going to deal with are very nice surface areas. And by that I mean that the shape that we're creating is going to be found by doing some sort of rotation. So something that allows us to have cross sections that are circles. That's the only type we're going to do in here. Surface area in general, you'd have to wait till you get to Calc 2, and you've got to learn how to integrate with vectors if you want to do surface area in general. Our voyage into 3 dimensions is always through a lot of symmetry. So we're looking at the simplest cases. So if we imagine that curve up there in quadrant 1, it's going to rotate around the x-axis and create that shape there. And we want to find the surface area of that. Well, there's a couple of things. First off, we do need the whole ds thing that we used from arc length. And that's exactly what we used right there. That is arc length, if you integrate it. That's arc length. So we're going to change that a little bit to build it up to surface area. And here is the idea. If you take a tiny little piece of this curve and you rotate it around, you get something that can be approximated by the frustum of a cone. If you take a single point, you get a circle. But if you take a tiny piece of arc and rotate it around, it's going to be like a ring. And this cone, you can imagine approximating it with this cone base. Call it a frustum. Does everybody see that? So the little piece of arc can be approximated by that ds that we drew when we were doing arc length, and when it rotates around, it creates this frustum of a cone. Well, the area of a frustum of a cone is 2 pi r ds approximately. So this formula, when you look at this, you should be seeing 2 pi r as the circumference. So if you imagine taking a single point and rotating it around, that creates a circumference, creates a circle, that's 2 pi r, and the ds is like the slant of a frustum. Right? We saw that ds approximates, back on the other slide, we saw that ds approximates the curve. So ds is acting like the diagonal on the frustum, and that's going to approximate the curve that's connecting the 2 points. So the only thing that we have to change is the following. So 2 pi r is the only thing that changes. Instead of arc length, all we do is put a 2 pi r out in front of it. It's 2 pi r ds. The integral of ds is arc length, and if we put a 2 pi r in front, then we have surface area. So we're in this boat again where, oh, the ds, we need to convert to dx or dy. And so that is what we're going to do with surface area. So we come over here. There's our generic formula, 2 pi r ds. We don't know anything about s. If we don't know anything about s, we've got to convert to x or convert to y. And so what we do is simply take the ds and we convert that to this, which is the arc length integral. And the radius is nothing more than the function. And when you look at that picture that we just had up here, the radius of the circle that you create, if you rotate this point around, you're creating this circle, and the radius is that distance there, which is whatever the function is that's given to us. So that makes it pretty straightforward. So let's try one. So in here, when you look at this formula, that is circumference. And that's how you want to think about it. It's the only way you'll remember it. So that's circumference, and this part you remember as ds. So circumference times ds. So let's try and see if we can do one of these. So here is that curve in the first quadrant, rotates around and it creates that looking thing, whatever that is. There's our function. So in your mind, you're thinking about, okay, this point on the curve, it's that far away from the x-axis. So let's find the circumference when you rotate around the x-axis. Let's find that circumference. So 2 pi r. So we're going to have that our surface area, I'll call it SA, surface area. We are going to go 2 pi r, so 2 pi. R is given by the function, so times 8 root x. And I'm not going to put in the d, I'm not going to replace the ds yet. I want to focus on the circumference. So this right here, oops, that right there is the circumference. So 2 pi r, that's the circumference. And then we have the ds, which we just did in the last section. That's arc length. So let's just write down the setup for this, and then we will be good. So this is going to be 16 pi to the outside. Our limits of integration are going to be 9 to 20, since they give those to us. We have square root of x. And then it's going to be the square root of 1 plus the derivative squared. So we just need to figure out the derivative of y. So y prime, bring down the half, and we're going to get 4x to the negative 1/2. So that's what goes in here. 4x to the negative 1/2 plus 1. And I'm going to write it as 4 divided by the square root of x.
Wouldn't it be 4 divided by the square root of x squared? The whole thing squared?
Oh, I didn't square it. Thank you. Thank you. Yes, absolutely. Thank you. Yeah, we take our derivative and then we square it. So the derivative is 4 over the square root of x, and then we square it. Yeah, thank you. And yeah, we'll stop there. We'll finish this one on Tuesday. But we'll see that that's going to simplify to a pretty easy integral overall. All right, well, have a good weekend. Do a ton of math. Be safe, have fun, but do a ton of math. See you all next week. Week 2 is done. Week 2 is done. Shockingly. Somehow week 2 is already vanished.
Es que si se estiró bien fácil, porque como